things we mentioned last time, we'll just go back to that for a second, is get entry. So if we were doing get entry on a list using using an array, then we said that it was O of 1. Right here it is, get entry. If we use the array implementation, then we can do a direct access, it's O of 1. However, if we are implementing our list using linked nodes, we know that we have to traverse through the list, and it's O of n. Okay? And we said we're going to be looking at sorting. Not everyone covered sorting in previous classes, or not many sorts. We mentioned that some of the inefficient ones are O of n squared, on the order of n squared. And we're going to be talking more about the order of and algorithm efficiency today. Any questions so far?
I actually had a question about the grading for the first phase. Is that going to be back to us before we submit second phase?
Yes, I did look at all of them. I have general feedback to share with you today, and we'll probably be finished grading by tomorrow. Let me actually, well, I'll talk about the algorithms first, and then we'll come back to the project, okay?
Okay, sounds good.
So, any other questions? Ready? Okay. So now I'm going to talk more about algorithm efficiency, and then we'll come back to the project. Here it is. Okay. Algorithm efficiency. Okay, so this is from chapter 10 of our textbook, and in the slides, it's essentially the highlights and the figures. I posted this so you could follow along here, or also in the slides that I posted, whichever you prefer. Okay, so last time we talked about algorithm efficiency, and we said that we'd like to find solutions that are the most efficient. What does it mean to be efficient? Mostly in terms of time, but it could also be space. We don't want algorithms that use up too much space. But how do we measure the efficiency of algorithms? Do we just run the programs on different machines? If we do that, then it could just be the speed of a particular computer. We could say it's very fast. So we can't tie it to a time. We can't say, oh, it ran for 1 minute, so it's good, whereas this other algorithm ran for 5 minutes, because we don't want to tie it to a particular implementation on a particular machine, on a particular operating system. It might be running other programs. So we never look at efficiency in terms of how long does it take in terms of time. Instead, we're looking at the number of steps. Is it O of 1, meaning it's 1 step? Is it O of n, meaning it's n steps? Okay. Okay. How do we measure it? So we don't want to compare programs. This is what I just said. We want to compare algorithms. So we can't just say this is how, I ran it and it's very fast. it only took a couple of seconds. It depends upon the computer, it depends upon the data. So instead, we're counting the number of steps. So for example, traversing a linked node. This is one of the examples we gave. So this is not our list example, but going back to linked nodes, for example, we had our bag was made out of, one of the implementations was a linked node. So this is, as long as our current pointer, which starts off at the beginning, doesn't hit the end, remember that the end of the list is indicated with a null, then we go ahead and get the item from wherever the current pointer is, print it out, and then we get to get the next. So in order to traverse through this list, in this case, printing out the contents of every node, it touches every single node. If there are n nodes, it's going to take time proportional to n. So if there are 5 nodes, it'll go through this loop 5 times. If there are 500, it'll go through it 500 times. Are there any questions on this so far, what we're counting? Very often, it's how many times do we go through a loop? The other thing that we saw is that we're measuring the algorithm's efficiency and how long it takes as a function of the problem size. So that's n. If there are n items in our array or n items on our list, sometimes it grows as a function of n. Sometimes it'll grow as a function of n squared, which is much, much less efficient. Another thing that we mentioned last time is that we are only interested in large problems. We're not interested in small problems. Why is that? Small problems meaning that the size is small. So if the size is that we're sorting, let's say, 10 items, then do we care about which algorithm we use? Anybody? Right? Peter says no, right? Right, it'll be fast regardless. It's too small to care about. Okay, so, and also some of the more efficient algorithms in terms of time require some overhead. And so it's not worth it to go through the overhead of setting everything up in order for it to be faster. It's sort of like, let's say you need to get from point A to point B, right? If they are very close together, let's say they're a block away, are you going to get your key and get into the car and pull out and drive 1 block? It might be faster to just walk the 1 block, right? Maybe you won't find parking where you are going. Maybe you'll lose your spot where you are. So it's not worth it. So if it's a small distance, then maybe you'll just walk it. It doesn't make a difference, right? If it's a very long distance, then you start to consider other possibilities. Is it going to be faster to go this way or that way? Is it going to be faster if you take a train rather than driving, right? So it only starts to matter if it's a larger size, a longer distance. Now this is a figure from our text, figure 10.1. So this is, again, the textbook gives us different ways to look at this algorithmic growth rate. So here's one. We have 2 algorithms, algorithm A and algorithm B. And we're told that the first one, they're both functions of n. At the bottom of the graph, we have values for n. So this would be that the size of the problem is 25 items that we're sorting, let's say, or 50. And it gets bigger and bigger as we go off. in the x, along the x-axis. The number of seconds, which we're counting really the number of steps, let's say, is along the y-axis. So this says that, let's say algorithm A requires n squared divided by 5 seconds. Okay? And algorithm B, to do the same, whatever the same function is that we need to do, algorithm B requires 5 times n. Okay? So which one is more efficient? Algorithm A, if you look at the graph, or algorithm B, as n increases? Okay, so we look at the number of seconds. Okay, let me go back to... So which one is more efficient, right? More efficient, which one takes less time? More efficient means it takes less time given a large n. So if we look at small values, less than 25, then we'll see that algorithm B takes more time for small values. But as soon as we hit 25, algorithm A starts taking much more time. Algorithm A looks like a parabola, and it's going to shoot up, whereas algorithm B is going along n, right? And that one is going to be more efficient. So the answer is B, that algorithm B requires 5 times n seconds. So even though for small values, it looks like A is better, for larger values, greater than 25, algorithm B is more efficient. It's underneath algorithm A. Algorithm A shoots up, and it's less efficient. Are there any questions about that? So this is an example why we don't, 2 things are being shown here. One is that we're not considering small values. Small values, as Peter said, it's not going to make a difference, right? For larger values of n, as the problem grows bigger, that's what we care about. The other thing that's being shown here is that even though algorithm A looks like it's dividing by 5, so it looks like it's making it much smaller, because it's dividing by a constant by 5, that gets subsumed when the value gets very large. It no longer makes a difference, that small value of 5. So, and the same thing here, if we say that this is 5 times n, we basically ignore any constants. So if it's 5 times n or even 100 times n, it's going to be subsumed as n gets very, very large. This will still be just a considered O of n. So do you see that? That constants, when we're comparing, will only make a difference up to a point, and after that, it depends if it's an n in the equation or an n squared. N squared is going to increase much more rapidly. So if we, as we increase the size of our program, the size of our problem, n, and if it goes up, if the algorithm then takes n squared times, as n gets larger, that n squared is going to make a very, very big difference. Any questions? Okay, so we said the big O notation is on the order of. So we could say that algorithm A is on the order of some function of n. And it's denoted as a big O in parentheses, and whatever the function is in the parentheses. Now we could have constants, k and n naught, n sub 0, okay? This says A requires no more time than K times f of n. So we have that constant K, which can be multiplying our function. And the time units to solve the problem, the size is going to be greater than n naught. So going back to our previous example, we're looking at greater than 25. When n is greater than 25, that's when it makes a difference. And the constant here was 5, and we're going to say that it's still O of f of n. So this algorithm B would be O of n, ignoring the 5. Algorithm A is going to be what? O of what? Anybody? Algorithm A is O of what? N squared. Exactly. Thank you. Amazing. I missed the last 50 minutes, and is it all possible to record lectures? Uh-huh. Okay, Laura, no problem. First of all, we didn't get so far, and the slides are posted. Okay, so you could look at the slides. But let me go over. I'm not sure which slide you were on when you lost connectivity, but we're basically reviewing what we talked about last time, but now with pictures, right? With the figures from the textbook, we said that algorithm A increases very rapidly as n increases. It's on the order of n squared. But algorithm B goes more slowly, and it's on the order of O of n. If you have questions, you could always meet with me. Okay, so here's another example. Here we have 3n squared for the graph that says 3 times n squared. And the second one has an n squared, but notice it also has an n in it. N squared minus 3n plus 10. Okay, which one is more efficient? The first one or the second one? Which one is more efficient? The first one, 3n squared, or the second one, n squared minus 3n plus 10? Which one is more efficient for large n? Second one, thank you. Great, that's right. Because we see that as n increases, it's going to be increasing more slowly than the first one. So even though it has an n squared in it and the first one has an n squared in it, because it also has an n, right? We're subtracting 3n, then that one is going to increase more slowly. And here is the graph. You could plug in different numbers and see that it's going more slowly. It's still going to increase after this, but not as rapidly as the 3n squared. Any question on that? This slide is very important, and it shows the relative growth of common functions that we'll be looking at in this course. And you'll also be seeing this in your algorithms course. And of course, O of 1 is the best, right? Takes one step, regardless of what the algorithm is, it takes one step to do. Now, not every algorithm can be done in O of 1, but last time we mentioned a particular function that's O of 1. And what was that? We mentioned a few of them that were O of 1. meaning that it could be done in one step. Right. So exactly, Naza, thank you. Stacks, push and pop, right? One step. Get entry, but can you be more specific, Unazia? Get entry only for which implementation? Get entries for our list. Which implementation was it O of 1 for? We mentioned at the beginning of this class as well. Only the array. Thank you, Bill. Right. Okay. Now there's also O of log base 2 of n. The log base 2 of n, of course, that's larger than O of 1, but it's smaller than O of n. Okay, so what was an example of an algorithm that was O of log base 2 of n that we've been going over? Right, we went over it last time, and we've been using it. We used it in one of our projects. It was with the area code. Okay, the binary what, Anthony? Binary search. Exactly. So the binary search, because binary is going to be used in so many different contexts. So to be specific, it's the binary search was O for searching for something was O of log base 2 of n. So of course that's not a direct access, but so it's worse than O of 1, but it's better than O of n, which would be a linear search. Okay. The next one on the list is O of n. That would be an example, we said, of a linear search. The next one, let's see, I finished my tea already. O of n log n, we'll see algorithms like that when we do sorting. So that's worse than O of n, but it's better than O of n squared. And of course, O of n squared, because you see O of n log n is n times log n, and n squared is n times n, so that's bigger. N cubed, of course, is worse, and then 2 to the n is the worst of the ones that are commonly, these are common functions that are used with O of n. O of, with the order of. Now, here we see it in a table form instead of a graph form. So here, going down, we have O of 1. Regardless of the size, if we go across, we don't care if there are a million values in our stack. It's still going to be O of 1 to do a push because we push at the beginning. If we have log base 2 of n, we see that it grows pretty slowly. If n is 10, log base 2 of 10 is 3. We go all the way up to a million, and we discussed this, if you remember, when we looked at my dictionary, my huge dictionary, we said 2 to the 19 is about a million. 2 to the 20 is about 2 million. So we can see that it grows, but pretty slowly compared to n, right? Look at n, if we look at for 10,000, log base 2 of n is 13 steps, and this is 10 to the 4, which is 10,000. It's a huge difference. And look, when we go up to a million, then of course n is a million, right? Because it matches whatever n is over here. And as we said, log base 2 is 19. We see a huge difference when we go between log base 2 of n to n. Now, if we're multiplying by n, if we look at the next entry in the table, n times log base 2 of n, then of course, each of these values gets multiplied by n. So if we look at the values, we're basically multiplying each of these. So if we look at, and this is approximate, if we multiply by n, by log base 2 of n, this is going to be 10 to the 7. It's always going to be more, one more, n times the previous one. Okay, so it's always much larger. N squared is a huge leap, right? So let's say for 10, this is 30, and n squared is already 100. If we move out all the way to the end, we have 10 to the 12, so 5 more zeros than the one above it. So it grows much, much more rapidly. And of course, n cubed is much worse, right? And 2 to the n is crazy. Look at this last value. So we really want to avoid algorithms that are 2 to the n. And we're looking for algorithms that are in the range of n log n. For the more complicated algorithms like sorting, we're looking for algorithms that are in the range of n log n. Any questions about this table? Okay, and as we go over algorithms, we'll try to assess what is their, how to analyze them and what is the big O notation for them. So the next slide is just a graph form of what we just saw in the table. Okay, now there's one very important graph that's missing. So we look at this. 2 to the n is the first one because it grows so rapidly, it's off the charts, right? Here's n squared. Sorry, n cubed. Here's n squared. This one way over here is n, and this is log base 2 of n. You could see why this one is very efficient because it grows so slowly. If you remember your log graphs, they level off like this. They go they increase very, very slowly. That's why we're looking for log base 2 of n in our order. Either for the searching, we saw it directly, and also we'll see in sorting that it multiplies n. Which graph is missing in this picture? Anybody see which one's missing? Oh, okay. No, but I'm saying it's labeled here and missing. Right. Right. It's n log n is missing. So, but it's in the book, okay? It's on page 315, and it's figure 10.4. And I guess it just didn't print here for some reason. It's not in this graph, okay? So where is it? It's labeled. It's in between here and here, and it's pretty much in the middle of
Professor, if you're pointing at the screen, we can't see it.
So it's where it's missing. It's between n squared, right? N squared is there, and n. It's in between those two, n squared and n. Okay?
Gotcha. Now I can see.
Yeah, it's between n squared and n. That one is missing on this graph. It is in the textbook, though. It's figure 10.3. In our new edition, right, these slides are from the previous edition. In the new editions, it's figure 10.4, I believe. And in the new edition, it's on page 315. Any questions on this? And why is log base 2 of n moving so slowly? Because remember, if you have, it's the inverse of 2 to the n. If you have 2 to the n, you want to see what value do we have to raise to 2 in order to get n. And so that's just the exponent. The exponent, if we go back to our table here, right, it moves very, very slowly. 2 to the 19 right, is giving us about 1 million. So that's why it grows so slowly. Okay, and then here are the things that we've said before. Ignore the low order terms. Ignore, for example, if there's n squared minus n. Ignore a multiplicative constant in the high order term. So if it's 5n squared, we're going to ignore it. Okay, and we're going to be talking about worst case and average case. Okay, that's the worst it could do. We'll talk about it, and the average case. We're most interested in the average case. The average case being that this is what it does if the values come in random order. Okay. So we'll see this as we go along. We're most interested in the average case when we talk about the efficiency of our algorithm. Okay, so keeping our perspective that we want to consider how often we use a particular operation. So for example, in our editor, how often do we do get entry? Anybody, where do we do get entry so far? Right, thank you, Janway, in display, right? However, the files aren't that big, and since we're using a link-based version of our implementation, it's going to be O of n. Now, why did we go with the link-based? Because we're also going to be doing which operations that are better for link-based than for array-based. Remember, we're going to be, thank you, Peter. We're going to be inserting and deleting, and for that, we don't have to move all of the, we don't have to shift all the values. Our particular list is not so efficient with link nodes, and we'll be discussing why that is. And later on in the semester, we'll discuss a more efficient way to implement our list. But again, keeping our perspective, if the problem size is small, then we don't care about the algorithm's efficiency. We also, it could be that it's fast, but uses up massive amounts of memory. And so we, depending upon our memory capability, we might care about memory as well. Okay. So last time we spoke about searching algorithms. This is a summary of it, that if we have a list of n items and we do a sequential search, the worst case is we'll have to go through all of them. But we said the average case is also O of n, because sometimes they're at the beginning, sometimes at the middle, sometimes at the end. On average, it's still, even if it's n over 2, that's still just a constant. It's still O of n. And the best case is if we find it right away, it's going to be O of 1. Binary search for a sorted array, that's what we did earlier on with our area codes. The worst case is log base 2 of n. So it's really wonderful. If we get it on the very first try, for that it's 1. But for the worst case, it's never going to be more than log base 2 of n. Okay? But we do have that required overhead. We have to, the array has to be sorted. Okay, so that's one thing to keep in mind. Any questions on this? As we introduce new algorithms, we'll be concerned and we'll be discussing their efficiency. And these slides are posted on Blackboard. Okay, any questions?
Professor, I know you said they were posted on Blackboard, but I looked high and low. Where exactly are they posted?
Okay, let me take a look. Okay, maybe.
I was able to find some other slides on a website, but I just wanted to let you know in case other people were looking for them.
Okay, hold on. Let me just take a look. Okay. Okay. I didn't hit enter. Could you just, thank you, Laura, for pointing that out. Can you check now? It should be under content. Right, there's interlude 4, and then there's algorithm efficiency.
Yeah, it's available now. Thank you.
I didn't hit enter when I was selecting it for some reason. It was open to that. So
That's okay. Christopher actually sent me a link in a chat, but I just wanted to make sure in case other students were looking for it.
Thank you. Right, you have access to this now. Christopher, where did you find it? All of these things are online someplace. The books. Christopher, if you want to post that, that would be great too. Okay. So now let's go back to our notes. Okay, so thank you very much. Yeah, the Corano PowerPoints. Thanks a lot. And it looks like the one that you have is for the 7th edition. So that's great. Okay, so now they're posted. Okay. So probably one of the most important slides that we saw, just to, besides all the graphs, let me just go back to it for a second. Let's see if I can copy this neatly here. I'm not sure it's going to copy well. You have it in your, there we go. Okay, so that's probably one of the more important pieces of information to remember. Okay. Now, just want to draw something as well. Hold on. Maybe I'll do this after the break. We're going to just review the different ways that we are organizing our data until now. Okay. Okay, so I'm just going to do this first, then we're going to take a break. So the we could organize our data, in general I'm talking about, using an array with indices. We could organize our data using linked nodes. Okay. Or another way we can organize them is using a list. Okay, so if we have data that we would like to search, let's say, for example, we could put them directly into an array, a raw array, which we said is dangerous because an array is really a pointer. We could put them in linked nodes. Okay, so for example, the bag was organized either as an array or as linked nodes. Now, what we're working on now is our list. And the list we saw could be organized as an array, or it could be organized using linked nodes. Okay, so if we directly put it into linked nodes the way that a bag was, then there are no methods for the linked nodes. Each method of bag created its own way of accessing these linked nodes. On the other hand, when we look at list, we make an instance of list, and list has its own methods. So we call get entry, and get entry, if it's implemented as a list, will do a direct access into our array. And if we did get entry on the implementation that are linked nodes, then it would traverse through to get the contents of that particular node. Okay, so I just wanted to emphasize, if we have a list, then a list is one more level of indirection, that we make an instance of a list and then we use its methods to, even if it's linked nodes, we use the methods in order to access it. So we could go back to bag. Let me just write this here. For example, this would just be an example that we could, so far we didn't do it this way. We only use the first two methods, but we could make a bag out of a list, right? So bag in its header file in the class could have an instance of list. And then for bag, if we wanted to call contains, right, it would have the same bag interface, but the implementation, let's say if we called it bag list, would call the methods of list in order to see whether it contains a certain value. Okay, so now we see we could implement bag many different ways. We mentioned that we could use a vector from the standard template library. So there isn't one or two ways to implement. There are many ways to implement something like a bag object. Okay, let's talk about stack for a moment. Stack, right, so over here, I'm going to put an or. Stack that we saw so far was implemented either directly as an array or directly using link nodes. However, now that we've learned about lists, we could implement a stack using a list. If we wanted to see if the stack was empty, we would check to see if the list was empty. If we wanted to push onto the stack, which method would we use for list? How would we push onto the stack? If we wanted to push onto the stack and it was implemented using a list, we could only use the methods of list. We'd have to go through the methods in order to manipulate our stack. So for example, if we wanted to do a push, does anyone know which method would we use from list? Insert, exactly. Janwei, can you go one step further? We're going to use insert because that's our only way of getting things onto our list. So that is correct. Where would we be inserting? Remember, our list is positional. So if we wanted to implement a stack using a list, where would we put it? Which position on the list? Okay, just to make it a little bit, okay, that's a very good guess. Okay, so Janwei says we should put it at the end. Aya says top of the stack. So Aya, can you go one step further? Where is the top of the stack if it's implemented as a list? -1 is what top is equal to in our array implementation before we put anything on it. Okay, so Janwei, the reason why we wouldn't want to put it at the end is that that would be inefficient. We could, but it would be very inefficient to do, let's say, top, to do a peak, to look at the top value would be very inefficient. We'd always have to go to the end. We'd be always, in terms of O, it would be O of N to do the push, O of N to do the pop, O of N to do the peak, where Aya said top of the stack. In terms of the list, where is the top of the stack? What position of our list? Maybe I'll draw a picture of it. 1, exactly. Okay, so if we insert into position 1, it'll put it at the beginning of the list. Perfect. Okay, so we see that we can implement our bag or our stack using a list. Yes. Okay, so here's our list. Let's say it currently has 3 items. Okay, we have a pointer to the beginning, which, remember, this is the list, and so the pointer at the beginning is called head pointer. Okay, but now we're doing a push. We're going to call insert on 1, and insert on position 1. Remember, first we do the link to the right, and then whatever that top pointer was, instead of pointing here, right, it's called head pointer. Instead of pointing here, we would update it to point here. and then it would no longer point here. And now our new value would be in position 1 on our list. Okay, so Aya, does that make sense?
Yeah, it makes sense, but I'm just a little confused because like that looks like a node implementation. Like I
Right.
thought we were doing stack. I don't. I'm a bit confused.
Right, so it's a stack using a list. So we have to call insert. In other words, we can't whatever our list is called. So maybe when we made the instance of it,
so a list by default is going to look like that, and then we're going to use like stack implementations. Is that what's going on?
so I want to just say it the reverse. Okay, this is what a list looks like, and we can make a stack out of a list. So if we have our class called stack, right? I'm just going to do this in pseudocode now. In private, we could have a list, whatever the parameter is, and we could call it a stack or the stack. So we're going to, inside of our stack, we're going to have a list. Okay, just like in our editor, we have a list. Every time we want to add something to our, using our editor, if we want to add to our list, we have to use the list operations. So going back to
And you're saying list to refer to linked lists. Sorry, you're saying list to refer to linked nodes, not linked list. I know you said they were different, but I want to clarify.
So now we're talking about over here, right? We're talking about a linked list.
Okay, it's a little difficult for me to tell when we're working with linked list versus when we're working with linked nodes.
So in the picture, we go back to here. This one is just linked nodes right here, right? These are linked nodes. And here I wrote the word list to show that it's the list object. So this is similar to what we did in our editor. In our editor, we have an instance of a linked list, right? In our book, it's called linked list. So let me just right here, linked list. Linked list. I'm going to write it a little bit more neatly. We'll be seeing it. It gets confusing because we could build objects many, many different ways. We just have to try to be clear about which way we're using.
Yeah, I guess maybe I'm a little still on. I know that we've gone over it, but I'm still a little unclear about maybe it's the big O notation differences that might occur between a linked list and linked nodes, since I mean a linked list really is just the implementation of linked nodes, right?
Well, remember, if we look at linked lists, we could implement it using an array. Right?
That's right.
Yeah.
Yeah.
Okay, so in an array, it's going to be, that was the first implementation we looked at for linked list in chapter 9. Okay, so the linked list can be implemented as an array, and it can be implemented using linked nodes.
Okay, would it be fair to say that linked nodes is a data structure and linked list is a implementation?
The other way around.
Oh, okay. But
okay, we're talking about
the bag, for example, like the bag is an implementation of like.
No, bag is a data structure.
Oh, okay. I guess I have that backwards then.
Yeah, bag is a data structure, stack, linked list. Those are all data structures. And then the lines here are talking about the implementation. So a bag could be implemented as an array. A bag could be implemented using linked nodes. And now, what I introduced one new idea that we could implement a bag using a linked list. Now, when we look at linked list, it itself could be implemented using an array or using linked nodes.
Yeah, I'm going to have to make a Venn diagram for myself later.
Okay. So the data structures are bag, that was the first one we looked at, stack, linked list. Okay. We're going to, when we get to, right now we're in chapter 10, and 11 is going to have talking about sorting. And then when we get to chapter, let me just make sure I'm giving you the right chapter. Chapter 13 is, chapter 14 is queues. When we get to queues, we'll also see that we could implement them different ways. 13 and 14 are queues. Okay, so here, if we were implementing a stack using a linked list, then when we did push, we would have to call the linked list operations, its methods, and as Janway said, we'd call insert. And we'd call it on position 1 in order to put it at the beginning. Okay. So how do we, let me just say, if I called my stack the stack, then, or let me just use the same color. Since I wrote this in black. Dot insert 1. Let me rewrite that. I think I'll type it. That would be our push. So the stack would be implemented as a linked list. Okay? We're going to come back to this. We'll be talking about this many times. But I just wanted to show you the different implementations that we are now, what have we covered so far? Arrays, implementing using arrays, implementing using linked nodes, and we could implement using linked lists, using the data structure linked list. And we saw this in editor, right? So let's just review that too. Everyone did this in their first phase. Under private, we had, for example, a string, and we called it lines. Okay, so there's an example of using a linked list inside a class. This is sometimes called composition. Where we are creating a new object out of an existing object. Okay, so we're creating a new object out of an existing object. So for example, our editor composes a linked list object. We have an instance of a linked list here inside of our editor class. And the same thing with stack that I drew up here, right? That the stack has a list as part of it. Any questions on this? Okay, so let's take a break.
Sorry, you just removed something from the notes. What was that you removed?
The editor, I did Control Z them, so the editor composes. Right, that the editor has this linked list object as part of it. Okay? Any questions on this? Okay, so now we'll take a break until 11:30, and then we're going to talk more about the editor, and then we'll meet in groups. Okay, but I want to talk a little bit more about what we're doing in phase 2. Okay, so we'll reconvene at 11:30. Okay, we're back. We're going to talk more about the editor now. Okay, so does anyone have any questions before we start? Okay, so I think I'm going to share with you, I'm going to stop sharing this and share with you one student's work. Let me just see what that is. Okay, let me just open it again. Hold on. Okay. I'm just going to share it in one moment. Okay. I think this one's it. Okay. So this is one student group, and I like the way they set up their loop, so I'm just showing it to everybody. This is, remember the editor has a run method. You might do this a little bit differently, so yours might not be exactly like this. So they place the cursor at the position in the upper left-hand corner. And this is what I'd recommended doing to a few groups, and this group did it. So to have a Boolean called running, let's say, that the editor is running, and it's set initially to true. And then the loop is while running. And then if the user puts in a Q, then you set running equal to false. Okay, so you're in this loop. This is the general idea. You might do it a little bit differently. This one doesn't have a switch statement, which maybe they're going to put in for the next part of it. But this is the idea. While running, you have it's true, and then if they put in a Q, running is false. Now it's going to be a little bit different because they're not going to be able to quit if they have made changes that they didn't save. Okay, but this is the idea. Any questions on this? One other thing about this one, since we're looking at this, in their editor.h, first of all, I'd put the public first before the private, right? And the other thing is that place cursor at is not in private, right? It's a standalone function, so it shouldn't be part of editor. It's not really part of the editor. You could have an editor running on a non-Windows machine, so it wouldn't have place cursor at using Windows functions. So don't make this a local function method. Shouldn't be a method of editor. And here's the linked list we keep talking about. This group called it file. We had recommended calling it lines because file is very specific to the IF stream. It has a different connotation. Okay, so I think it should be called lines because it's a line editor and it's just holding every line. Happens to come from a file, right? But this isn't a file. Okay, that's one other thing I want to point out. You want to use meaningful names that makes sense, okay? Just giving some feedback in general. Otherwise, people did a pretty nice job of putting together the first project. So let me stop sharing. Any questions? So let's go back to our notes and talk more about the editor. Let me share my notes. Okay. Okay, so in this iteration of our project, we're adding in deleting a full line and also deleting single characters. We spoke about that a lot last time. If you have questions, please ask me. But another thing that we're doing is the color coding for the keywords. So the keywords are all the keywords for C++. And let me just make sure that that's visible. Hold on. So under phase 2, I just want to add on the file that we'll be using, which is the keywords. Yeah. So here are the keywords, and so I added it to the that file, and let me just stop sharing this for a moment and show you the keywords. So, Laura, do you see it under the assignment?
I'm checking right now.
Okay. Did someone raise their hand or ask a question? Because it was behind whatever I'm doing.
You said it would be in assignments?
So it's under this assignment, phase 2.
Yes, I see keywords.txt.
Right. So let's look at that.
Okay, I didn't realize keyword coloring was part of this phase.
Yeah. Okay, so it's I'm giving you all the code, so it really should not be that hard. Okay, so these are a list of keywords in C++. And so you're just going to read this file in your program and keep it in an array. Why do we want it in an array? Right? We're going to be searching to see if Chris, are there any questions on these keywords? It's just a list of keywords. You're going to read it in and read it into an array. So that's in the project, okay? And in addition, I also posted, let me just go back to that. Okay, under content code, remember we had place cursor at, but there's also going to be color text. Okay, so color text is now there, and that is the Windows code that, given a value, will put that color on the, will change the color. Okay? Okay, so Deanna asked, should we add it to the editor.cpp file? You're talking about the code to read it in, right, Deanna? Yes, yeah. So you know that you read in the file from the, that the end user specifies. Also read in the keywords. This will be hard-coded for now, right? Keywords.txt. It's not going to be in the command line arguments. So it could just be in the constructor of the editor. Just read it in. Read in the keywords into an array. Now, I asked, why are we reading it into an array? Why into an array?
For searchability.
Right. Specifically, we're going to be using the binary search. So, and so we'd like it to be, right, we're going to, and notice I think I put them in sorted order. So if they're in sorted order, you don't need to sort them, okay? What else? One more thing that I added on is the code to display lines. Instead of just displaying the lines as it is, I wrote some code for you to use that looks at it a word at a time, processing the line word by word, and then I have the code there for you to look it up in the binary search and see whether it's a keyword or not. So if you look at that code, you'll see that it calls this color text with a 1 or a 0. So if it's a keyword, it's going to color it blue, and otherwise it's going to leave it alone as black. Okay, so you have 3 new things. You have the list of keywords is posted. You have something called color text. This is similar to place cursor at, in that it's Windows code, and it's not a method of editor. It's going to be a standalone function. And it calls something called set console text attribute. Let me just share that with you. Okay, so it gets an integer value. In our case, it's going to be 1 or 0. And it's going to call this set console text attribute. This is Windows code. So I'm just giving it to you. And you're going to take whatever value, 1 or 0, and add it to 240. Okay? Some of you might know that there is RGB codes to specify colors. Okay, so here, the difference between blue and black is 1 value, so it's a 1 or a 0 to make it blue or black. And the other thing that I just wanted to go over with you briefly, it's the new display lines. So let me share that with you. Okay, so this is again under code. And here's the new display, an updated display lines that I wrote. It says go through notice this position here has to do with the position in the line. Okay, it might not be the best. I just want to make sure you don't think it's the position within the list, right? This is the position within the line. So for each line, it goes up to line's length. And here is the next line. It's looking at the lines, .get entry, and it's looking at the particular position, right? So let me say that reversed. I just said it reversed of what I wanted to do. This is going through a line at a time, but now I is going to go through each length. So the outer loop is an outer loop that's going through the position starting at 1. Lines is in the editor, the linked list. So getting the length of that. And each time through this outer loop, it goes through each line one at a time. And I should put comments in here, so I'm going to do that. I'm going to put in comments.
And this will fully replace the display lines we've currently been using?
Right. Yeah, I'm just going to put in a comment. So here you'll have the comment right away. So this loop, and so the outer loop goes through each line, and next line is going to refer to that. Let's make this. Now the inner loop is going through each line at a time. Okay, so it says while I is less than next line dot length. So this is next line is a string. Isolate, oh, here I have a comment, right? Isolate a word at a time. And remember, it can contain underscores. Some of the keywords have underscores. So I check to see if it's an alpha, because I want to ignore blanks and carriage returns. So if it's alpha, and then this goes through next line sub I, as long as it's either equal to alpha or an underscore. Here, this plus equal, remember, is concatenation, and it's going to create a word. When I leave this loop, I go ahead and call the binary search, looking at my array of keywords, right? Looking at my array of keywords. Starting from 0, I have another variable, keywords, the number of keywords. And then if it is there, remember that binary search returns a -1 if it's not there. So if it's not equal to -1, means that it was found. Therefore, it is a keyword. Color it, and this will color it a blue. Otherwise, turn it back to black. And here is printing it out. Instead of printing it a line at a time, we're printing it a word at a time. Now this if is if it's an alpha, and the else is if it's not an alpha, if it's not an alpha. In that case, go ahead and just print whatever character it is. Okay, so it could be semicolons or commas or blanks. Any of that will just be colored black. Go to a new line, and then here, this place cursor at is the user position. Okay, so the user position is wherever the user was, make sure that the place cursor at puts them at their correct position. Are there any questions about this?
I have a question for the keywords, because it's a static length and you said we're kind of hard coding it right now. Can we just count the number of keywords and make an array of that exact size, or would you like us to do code that would calculate the size for the array?
Well, you're reading it in, so as you read it in, you can count the number of keywords. And then you can make a dynamically allocated keyword array that's exactly the right size. So you don't have to hard code it, you don't have to count it, because you're reading it in. So you know exactly how many keywords there are. Does that make sense?
Yeah, I guess I was just asking if it would be okay to use a static array rather than a dynamic one.
Well, you see though that you won't know how big it is.
Right.
Unless you count it, and that's,
Yeah.
Why should we count when we could program, right? In some cases, when we make an array, we really don't know how big it is, right? We can't figure it out ahead of time. But here, if we're reading in a file, and we're not changing the size of the file, then we might as well get the length as we're reading it in.
Sure.
Okay, so you could read it in. We mentioned this with other examples too. You could, like we did with array codes, with area codes, you could read it in once, just counting, make your dynamically allocated keywords, and then read it in again. Make sure to close the file and open it again, so you're back at the beginning. Read it into your array. So you have an array called keywords, and you're going to read it into that. Any other questions? Okay, so you're going to this way. I'll mention that if you have a file that has keywords in it, then if you delete, let's say the keyword is while. And if you delete the W, then it's going to no longer be a keyword. It'll be Hile, H-I-L-E, right? If it's the word for, and you take away the letter F, it'll be or. So it'll start off colored, and if you remove one of the characters, it will change colors. So you'll see it right away. Did it work? Did it not work? Okay. Now I recommended last time that you first do X, then do DD, right? Then do W to write it out, and now do keywords. So do it in that order. Write it incrementally so that you're not overwhelmed with so many changes. Okay? Are there any questions about phase 2? I purposely didn't put a due date on it. I'm going to see at the end of today, after you meet, how far everyone gets. Because, is alpha is a built-in function, and it returns true if the value is alphabetic, if it's A, B, C, capital or lowercase through Z. Okay, so that's is alpha. Yeah, very convenient to use.
You said that there is no due date, but it does look like the due date is for today at 11:30. I just wanted to let you know.
It might have defaulted to that.
Yeah.
Yeah. Okay, so there's no due date for now. I'll try to go back to that and see why. Might just default to that. This is under group exercises. It's phase 2. And on mine, it doesn't say that there's a due date. The due date is blank. You might just have when it was made visible or something. But I don't have a due date on mine. Does anyone else see it?
You know, I'm misreading it. That's actually for last time it was modified. I'm sorry.
Right.
Okay.
So right now there shouldn't be a due date on it.
Great, my bad.
And okay, yeah, thank you, Deanna, Victoria. Right. So so there's no due date yet because I want everyone to feel. I don't want you to feel stressed over this. I want you to feel comfortable. Try to get as far as you can today. How many of you have implemented some of it already? How many of you have done, let's say, X or DD? Anybody? Any group get that far? Oh, so great. Okay, so that's great. Any other group? That's one group. Anyone else did? Oh, great. Okay, so people are getting through this. That's great. And you'll feel very good when you have the color. And I gave you all the code for the color coding. Hopefully it'll all work. And it'll feel very good when you delete a character. First of all, when you display it, if you have keywords, then they should show up in blue, right? That's without doing anything, just putting in the new display and make sure you have the color code there. So those two things by themselves, and of course, reading in the keywords, as Deanna said in the, I want to make sure, Deanna, did I answer both your questions? Or you only had one question, right? Okay, so.
Sorry, just one more from me. So the when we read in the array of keywords, that should be done in the same constructor where we read the file in. Is that right?
That's right. But it's not in the command line arguments. It's hard coded. The name of the file, because everyone's going to have the same keywords.txt.
Yeah.
You're going to put it into the array. Okay, so now you have it in your array, and then the display lines is going to call the binary search. So you're going to have to also take your binary search that we already did and just move it in to your editor.cpp, not as a method, but as a standalone function so that the code is there, because it's not a built-in function. So you have to make sure you have that. Let me just write this in the notes, and I'll share the notes. So write down the steps. Okay, so for keywords, we're going to read in the keywords .txt. Read it in the editor constructor. Okay, and then we're going to read into put into an array, and this can be dynamically allocated. If you can't figure that out, just for now, don't make it dynamically allocated. But that's ideally put into an array. That array has to be accessible both in the constructor and in the display. So that keywords array has to be where? So that it's accessible.
Editor.h.
Right. So it has, exactly. So it has to be in editor. Right? It has to be in the editor class file. That way, different methods can access it. They read in the keywords. The keywords are in the assignment. Put it into an array. It's already in sorted order. Okay. Use the new display. Use the new display lines, and that should do the color coding. make sure to place the color coding function in. It's a function, not a method. It's the same as place cursor at, the same idea. And remember to place the binary search function in editor at CPP. It's also not a method. Hey, did I forget anything? This is also all to get the keywords going. Right, so I'm recommending the order. You don't have to listen to this. It's just what I think is the easiest. As soon as, right, if you get X, and DD, and W, colon W is going to just write back the file that you already used, and then do the keywords. As soon as you do the keywords, if you already have X working, then you'll see you can turn them on and off. Now remember, we're only doing X and DD from the beginning of the file so far. We're not navigating yet. And so if you want to check if it works, make sure you have some keywords at the beginning of your file. You could always change your file. Any questions? Okay, so we're going to go into groups, and you have to rearrange yourselves into the groups.